So what I want to talk about is something that I just figured out last year, why time is evil. So time, it's a little bit subtle. It's not timing of messages. It's a little bit more subtle than that. So this talk is going to be partly intuitive, partly technical. So we'll see. So what I want to do is understand really what time means in a distributed system. And it's kind of subtle. It's not just message delays. It's more subtle than that. I'll show you some examples of programs. And then I'll show you what it means for the designer. So there's a concept called an interaction point, where the program interacts with the real world. And I'll show you how to design with that, a simple design language that'll help you think about that. I'll talk a little bit about eventual consistency, which is one of the bugbears of distributed programming. And then at the very end, I'll give a challenge to Erlang and Elixir people. Okay, so actually it fits with Gnosticism. So you'll see how this works. Gnosticism is a very strange competitor to Christianity in the early years of our era. So basically, we're living in a small pocket universe called the Kenoma observable universe, but the real universe is the pleroma, the fullness that has all the concepts, ideal forms, but it does not have time, no time. So we have time, but time is artificial. Time is evil. So this is actually an interesting analogy to what I'm going to be talking about. So you want to go beyond time and only use time when you really have to. Evil things you want to minimize. But since we're living in this observable universe and we can't get out, the Gnosticists, they want us to get out. They say we're prisoners here. We have to get out. But it's very hard. So basically we're stuck here. So we're stuck with time and we have to learn how to use it. Okay, so that's kind of a philosophical underpinning. But let me now start with a motivation, with some intuition. Let me go really down to earth and talk about poker and chess. So programming is a lot like mathematics. Superficially, there's a lot of formality, but it's actually fundamentally different. Programming is computers, they're artifacts in the real world. But mathematics is just symbol manipulation. It doesn't have anything to do with the real world. So what I say is prologue is to mathematics as poker is to chess. If you've ever played poker, you know that it's only interesting if you actually put real money into it, okay? If you're just playing for fun, it's nothing, poker. It has no interest. It's only interesting when you put real money. So the real world connection is very important. And the same for programming. So what real-world property is important for programming? And it's time, and we'll see that. So let me slowly introduce things. What I want to do today is I want to build a bridge between two communities that are kind of separate, the distributed systems community and the programming language community. There's actually not that much interaction between the two, not in any deep sense. Of course, people are building abstractions, and there's languages for distributed programming, but they just scratch the surface. There's really no deep connection, and the communities really don't understand each other. So in this talk, I want to make a connection, and I want to show you that really what language can give you, and there's some real powerful stuff there for distribution, not just abstractions. And actually, it's a big thing you can do. And it actually fits with the Erlang community because at the end I'll give you a challenge. There's a way for Erlang to make this, possibly to make this step. So let me talk first about functional programming. So it's confluent reduction of an initial expression to a final result. So basically a very mathematical way of programming. It has extremely strong mathematical properties, reasoning, debugging, testing, whatever. It's really amazing. Also for concurrency, parallelism, distribution. And actually, I learned there is really no efficiency penalty. There was a long debates on whether you're paying, but you're not paying any inefficiency. The problem is, though, it cannot interact with the real world. A functional program, during the execution, so the reduction of a functional programming that is done in time. Each reduction step takes time. If you want to interact, then during this reduction, you have to accept things from the world and put things back into the world. But that's not part of the definition. You can only do that if you could put these interactions in the initial expression. But you can't do that because you don't know them then. It's part of the real world, though you only know things gradually. So functional programming is very powerful, but it cannot interact with the real world. So sorry, functional programming community. That's the way it is, but all hope is not lost. So there's the other extreme, imperative programming. So we want to interact with the real world, of course. So you need to add, receive input, and so on, interact. We can do that. We can extend this model to do that. But in the same time, in the same breath, we lose all the good properties of functional programming, almost all of them. So there the question is, we have these two extremes. We have the pleroma functional programming, the ideal, and we have the observable universe imperative programming, which is really a mess. Okay, can we have our cake and eat it too? But you can't have one model that really does all the good things. So what can we do? So this is something I want to talk about today and put it in the context of distributed programming. So the idea is very simple. You want to write most of your program in functional programming, and you add small pieces of imperative programming exactly where you interact with the real world. And actually, we'll see there's only very few of these places. Even if you have a huge big data application running on hundreds of machines, you might think all messages are passing. There's actually only a few places. You can usually count them on the fingers of one hand where this really has to interact with the real world. So that's what I want to talk about. Also, existing systems. So this is for building new systems. Existing systems, unfortunately, they didn't really realize that. So they have these interaction points everywhere without even thinking about it. They're doing it everywhere, so they're a mess. So you want to remove these interaction points, okay? You can actually judge existing systems, how often they unconsciously interact with the real world. So let me give you some examples. So a key example is the humble client-server application. So client, you have many clients talking to a server. They send messages. Nice distributed application. This application cannot be written in pure functional programming. It's impossible. The problem is that the server has to accept input from any client without interference from the others. So there's liveness. Okay? If client 1 sends a message and client 2 does nothing, then it has to accept. If client 2 sends a message, it has to accept it. So you cannot determine in advance the order of the request. So there is a fundamental non-determinism here. But this could be a large program, and a lot of internet applications are sort of like this, where you do people at home buying stuff on Amazon or whatever. In this huge application, there's actually only one point where there is interaction with the real world. It is the point where the server accepts messages. That's the only point of interaction. The non-determinism depends on timing, is an interaction with the real world. This is what I call an interaction point. It's part of the system where the timing actually affects the result. So sending messages between nodes takes time too. It does not affect the result. We'll see. But an interaction point, here the exact timing affects the result. There's only one in this application, but you cannot write it in functional programming. Okay. Now, you can look at other distributed algorithms. I don't want to go through many distributed algorithms, but you can look at distributed algorithms and see interaction points are everywhere. It depends on the algorithm. So here's kind of a list of some of the important distributed algorithms: reliable broadcast, shared registers, consensus, causality, synchrony model that you run on, partial synchronous like internet, or fully synchronous like local area networks or cluster. So some of these things have interaction points. So I'm not going to go through all detail. You can read it later at your leisure, or maybe you have the slides already. Just a few things. For example, some algorithms don't. Reliable broadcast in distributed systems means that either everybody gets the message or nobody gets it. There's no interaction point there. There's no interaction with the real world. Shared registers, like distributed database, shared registers, very often there's interaction points. There's not if it's complete global single image, like linearizability, but if you have other kinds of things, like sequential consistency, you can have the nodes be kind of shifted. It does have an interaction point. The exact timing can make a difference. Consensus, which is like a key algorithm for many systems, unfortunately, it has an interaction point because when many nodes propose a value, there has to be an agreement on a value. But which value? The value that is chosen depends on precise timings. Where is the majority? You're getting a majority of nodes. That depends on precise timing. It is unfortunately an interaction point. It's an open question for me whether you can actually get the same power as Paxos or Rafta, so consensus with only minority failures on partial synchronous system. Can you do that with 0 interaction points? I have no idea, and I don't think so, actually. Doesn't smell like it. So this interaction points are everywhere. Okay, so we want to design with that. So I'm going to show you what is a distributed system that does not interact with the real world, and how do you make it interact exactly where you want it. Okay, so you want to design distributed systems where you know where the interaction points are. As far as I know, no existing language lets you do this. Nothing. Doesn't exist. So today, I want to define a very simple, kind of what I call design language. Has no implementation, has nice little pseudocode, simple, easy to understand, and you can design in it and then translate it to whatever language that you're actually programming in. So I think this is a good approach because this little design language doesn't have all these compromises. It's just concentrating on the functionality and the interaction points. And it's kind of future-proof because it's always going to be like that. So we're going to have a design language. But unfortunately, many people are stuck with very bad legacy languages. Most of you, hopefully not. I'm not talking about Erlang here. I'm talking about Java-like stuff. So basically, you want to hide it. So for these people, it's very hard, I think. The distance is very hard. For you guys, the distance is maybe shorter. And I'll show you. At the very end, you'll see, and I'll give you a little challenge for the Erlang community. So we'll define it in 2 steps, our design language. First step, we're actually going to define a distributed functional concurrent language that runs distributed programs and by definition has 0 interaction points. So that's our basis, our nice distributed functional language. And then we will have just the ability to add interaction points, and this is what I call multi-agent concurrency. I just want to give it a name. So this will let us do a lot of really useful thinking and design, and it will map directly to real languages, okay? You have to be careful about real languages because they always want to add interaction points, these real languages. So you have to kind of be conscious of that. But otherwise, the mapping is pretty straightforward. So the first step, we want to write distributed concurrent programs that are purely functional. So I'm going to start from the basics. I'm going to show you Lambda calculus, the basic of functional programming, and then we will immediately make a step up, give you very convenient syntax, and then in the second step we add interaction points. So here is the venerable, but it's still very useful definition of the Lambda calculus. So I'm not going to go over this in detail. I just want to show you this because the point is we have to think from first principles. So Lambda is the first principle. And so this is a calculus where everything is defining and applying functions, and there's no mutable state, and you can do everything with this. So you can encode all your data structures, control structures with this. So I'm not going to go this in detail. I'm going to immediately make a step up with this. So data types and control structures, you can define them in the Lambda calculus. You can code them. You can also add them. It doesn't change anything essential. So for us, it's OK. You can assume whatever you want. And then the second point, this is the key property, which is called confluence, the Church-Rosser theorem. This is really the key property, why Lambda calculus is still interesting, why there's no time in it. The final result of reduction is the same, no matter what the reduction order is, no matter what the scheduler decides to do. The scheduler is an evil demon. It's living in time, trying to break your program by making weird choices on the reduction orders. Well, the scheduler cannot break a functional program. Okay. And many variants of Lambda calculus have this property. So this is a key. It's really strong. And I want to leverage this for distributed systems. So you'll see how we leverage this. Now, the third point. Okay, so Lambda calculus, so we have a good foundation, but I don't want to use the Lambda syntax. It's really a mess. It's too hard to encode everything. So I'm going to introduce a more convenient syntax, network of concurrent agents talking to each other. So here's a more convenient syntax. So I just invented this. So I defined three concepts: agents, streams, and threads. So an agent is just a tail recursive function, and I can execute it in its own thread. A stream is just a list, but it's being read by one thread and being created by another. So it's not created all at once. So there's concurrency. And the thread is just a restriction on the reduction orders. So it's just information to the scheduler. So this program that I'm showing you here is actually a simple functional concurrent programming. It's just pipelines. It's pipelines of streams. I produce a list of integers. I do a map. So the input stream is mapped. 1, 2, 3 becomes f of 1, f of 2, f of 3. And then I'm doing cumulative sum. So I'm just introducing some notation that I just invented. Smart listeners will see that it's just a more readable version of a part of Oz, but with some variations. But just to make something very readable. And then you have the main programming up at the top. It's just threads. So this is actually just syntax for the Lambda calculus. So this thing is totally confluent, beautiful, pure. Okay. Now let's make it distributed. Now we're going to distributed systems. It's very easy to make Lambda calculus distributed. Just put each piece of a term on a simple node. So we annotate the terms with nodes. You have a set of nodes n. Each term is localized on a node. So the three reduction rules are the same because we assume that the computation is happening on single nodes, the alpha, beta, and eta. And then we add another one, which I call mu conversion for mobility, basically where the term changes. And you can actually implement this with pointers and so on between remote pointers and stuff. But again, I want to bring the syntax up. So this keeps the good properties. So now I take the same example I did before, completely pure. But now we put each agent, each executing thread, on a separate node, node 1, N2, N1, N2, N3. The streams will now be whatever, TCP connections, IP, whatever. There'll be ordered messages. So here we have a nice pipeline distributed programming, but it's completely pure. It doesn't matter how long the messages take from N1 to N2 and so on. The precise timing makes no difference because the result is always the same. So this is a program that has no time. It's timeless, time-free. It's pure. Okay, so now we have a pure distributed program language. Now we add interaction points. Again, let's start with Lambda calculus. So we want to add interaction points. So interaction points, it's where you actually interact with the real world. So basically, it's interfering with the reduction, and it can change the result. So mutable state is an example of this. But not only, nondeterminism, where you wait for several things, the timing is important, is also another example. So we'll do that, and also we'll give it a convenient syntax. So basically, we'll have our distributed function language, we'll have little interaction points. Okay? And then I'll show you how you can do client-server with this, and you'll see exactly why there's only one interaction point in that whole program. Okay? So here is what I call the read-write distributed Lambda calculus. So again, we're extending the Lambda calculus. We add read and write operations. So if you look here, so we keep the same rules as before. We have this fourth and the fifth and sixth one, which is if Greek letters are good enough for church, they're good enough for me. So I add sigma reduction and row reduction. So the send and a receive. If you notice the receive, it looks like a function application, a row x t1. And it's basically applying a function, but the argument appears magically, T2. You see that T2 on the right? It's not on the left in the last rule. So it appears magically. What does that mean? Well, it means it's messed up, okay, if random data appears in your program. But that's exactly what imperative programming can do. So where does that T2 come from? Well, it could be the right that is the closest in the past in the reduction sequence. So this sigma rule, the fifth one, sigma t to t, it looks like identity function, huh? Sigma t goes to t, but the t is actually sent. And the row can actually receive the t. So this, you can see this as send receive. You can also do mutable state with this. So this gives you interaction. You can see why it's messy, because the row reduction basically gets data coming in. And where does that data come from? Well, maybe it comes from sense, maybe somewhere else. So it messes up the reduction, okay? So these last two rules, I mean, I talked to some language theoreticians and say, I'm adding these two rules. Says, why are you adding those rules? You're messing everything up. Says, yeah, well, that's what imperative programming does for you. Okay, but you want them, so you have to put them in the language, but you want to do a minimum number of these. So now let's make, again, a convenient syntax. We'll start with our agents, streams, and threads. We add interaction points. So let me do it in a way that's intuitive, connected to our client-server example. So there's many ways, of course, to do it. Huh? It's sort of like send-receive. Huh? So I will add what I call a named stream. So basically a send operation. If you look here, I added something called a port. So the name comes, it's inspired by work. People worked at 6 who were thinking about this concept already in the 90s. Okay. And name P for stream S, new port S. So S is just a list that's being created, stream. If I do send px, I will add x to the list that's being created. Whenever you do the send, it just gets added. So you can do multiple sends in multiple threads, multiple parts of your program. In what order do these x's get added? In whatever order the scheduler wants to do it. So this is kind of messy, huh? The result of this depends on precise timing. Well, that's exactly what an interaction point is. So with this, we can actually get a nice design language. So with this design language, most of the program will be functional, and there will be just a few interaction points. So this actually seems to me to be sort of, so far, as far as I understand, the best paradigm for writing concurrent distributed programs. Okay, so let's go back to our client server. Now we can actually define it. So this is actually really interesting to read this code here. So you have that point where the server reads the 2 from the clients. You have one interaction point. So in the program, you create the server. So I call thread, I call it node. The clients and the server are executing on different nodes. So I create a port, new port S, and I start my server with its initial state and with S. So the server is, if you look at the server code bottom, a pure functional program. So server definition will read S. Q is the query coming from the whatever client that did a send, and T is the tail of the list. And then you call the server by doing some function, the server business logic, FS, and it's recursive. So basically, the server now is a pure function. Okay? If you look at the client is just a recursive functional programming, and each time it does a query, so it's kind of a skeleton code here. I've left out some stuff like ifs and stuff to make it simple. So the client sends a query to P, and then it calls itself recursively with FC of state, so it has its own business logic. FC is also a pure function, and of course, you can have messages coming back in the other direction. So I just want to show the messages going there. If they come back, they don't actually need an interaction point, because the client always knows it'll get messages from the server, so there's no non-determinism. So you see in this whole program, everything is functional except one thing. There is one port, one interaction point, and I do it in red there. And so in the program, that interaction point shows up as these two statements. In the actual architecture of the system, it's one single point. You could have 1 million lines of code there, but still it's just one single point, okay? So this, for me, this lets me now start building distributed systems, and I know where to put the interaction point. I tried to build them completely distributed functional way. That's where I try to do that, but whenever I need to interact with the real world, so for example, failure, I'm not going to give all the possibilities where there's interaction. Failure is an interaction because the timing, you never get messages. Never is a time thing. Non-determinism depends on precise timing. The result changes depending on precise timing, okay? So these things are interaction points, and you'll see them specifically in your program. So now we can start designing distributed systems in a nice way so that we actually know precisely where they're interacting with the real world. We can write most of the programming in this functional concurrency, which has 0 interaction points, and we add the interaction points as needed. And usually, you only need very, very few, which is kind of amazing, a very, very small number. And which is good because they get messy, these interaction points. So now, let me give you a simple case study. So eventual consistency is a messy thing. So I'm not going to go over all of the possibilities. I'm just going to give you some important insight. So eventual consistency is opposed to strong consistency. So eventual consistency in a database. So for example, here you have a database where you have replicas of the data. You have reads and writes coming in. So in eventual consistency, you can have multiple operations initiated concurrently that are in flight simultaneously, and you try to return the result as quickly as possible. So speed is the thing, okay? The writes will eventually be propagated to all the replicas. The reads will be eventually handled by at least one replica, and that's it. And what's the semantics of this thing? Who knows? Huh? Normally, when you write, things will get written. When you read, normally you read them, but here, speed is everything. Okay? So assume here in this, for example, you have a write, and immediately after that, you follow it by a read without waiting for the write to finish. Does the read see the write? Well, sometimes it does, sometimes it doesn't. Sometimes if you do 2 reads, the first one will see it, and the second one will not, or the first one will not, and the second one will. Actually, that's all of those things are possible. They may be rare, but rare is possible, huh? So it's kind of messy. So how should we think about this? Well, we have to focus on the interaction points. Where in this, if you want to write this thing as a functional program, what does that give you? And where does time make a difference? Well, time makes a difference at the replicas, because replicas will be receiving messages from different nodes. So if designed in a naive way, each of those replicas will have an interaction point, and you're kind of messed up. So how can we improve this? There's many ways, but I just want to talk about one way now, because which is a way we've been doing in our project. But there are other ways, of course. So basically, you want to remove interaction points. So for eventual consistency, for example, you could use strong consistency. You could change the algorithm. You might want to use quorums, for example, where you read and write to majorities so that the read will always read the most recent write, but you're kind of giving a performance. You also have to add causality if you want to really make it good. So it's not that simple. Another approach is more inspired by functional programming. This is the approach that we were using in the project. So actually, the whole business of interaction points was initiated when we were thinking about what does this really mean. So there's a kind of distributed data type called the conflict-free replicated data type, CRDT. So invented by group of people around Mark Shapiro's group. This is a very nice data structure. It's used in many systems. In a previous project, we were developing libraries for this with Basho and Riak database. Okay, so this was all written in Erlang, by the way. So these data types are very interesting because they are completely functional and monotonic and confluent. That means when you add information to a CRDT, it doesn't matter in which order. So normally when you update a data structure, you have information coming in, like you're writing to a register. Which write comes in first wins, the last one wins, and the first one is lost. So the result depends on the precise timing. But in a CRDT, that's not the case. The information is merged in a way, in a functional way. So you can say, well, this has limitations. Actually, it does, but it's extremely general, and you can do many things with this. So with this, you can define another kind of consistency, which is kind of in between strong and eventual. It's almost as fast as eventual, but it's much nicer than eventual. So we've developed systems. So this is in the project, the Sync-Free and now the Litecoin project systems. So Swift Cloud was one of the first systems, Antidote system. So we have really nice behavior. So reads will observe previous writes. Successive reads would observe increasing writes. So basically, you never lose information. Writes applied are only applied after observed reads. So you have a really nice, much nicer behavior. And it's still a completely asynchronous system that is very fast. Okay. So what I want to do now is I want to, again, get a little bit formal. So I want to make this a little bit more precise. So a lot of people talk about eventual consistency. Few people know exactly what it means. So I want to tell you what it means. So this actually is inspired by a really nice book, which I recommend, called Principles of Eventual Consistency by Sebastian Burkhardt. Highly recommended. It's free, PDF. You can get it immediately. And it's very readable, okay? Extremely readable for a book that's based on formal systems. So here's how they define eventual consistency. So it's actually kind of surprising. So I have objects and I have events. So the object could be like a database and I'm writing and reading, okay? Or there could be replicas of a database. I'm writing and reading. So basically, eventual consistency means that operations are intermittent before they become permanent. That means you do an operation, and if you do another operation, the second one, it might see the first one, or it might not, okay? And then you do another operation, it might see that first one, it might not. So if you do a write, if you do a read, it might see that write, might not. Okay, and then you do another read, it might see that write, it might not. So you have this weird intermittent behavior where the read kind of, sometimes you see it, sometimes you don't, until the whole thing settles down. So the formal definition is, so for an object, when you do an event on that object, so that's the E, you read that formula at your ease, I'll just give you intuition. I do something, then when I do further events, a finite number of those will not see that first one. But if it's finite, so eventually, okay, everybody sees it. But during that period when it's not completely done, the system can be weird and fluctuating. Okay, so that's kind of really messy. So convergent consistency is much better. And this is because it's taking this functional approach where you only add information and you never change information. So whenever you do an event, okay, once you see it from another one, you will always see it. So basically, the information, it still can take some time before you see it, but once you see it, you will always see it. So when you do a write, and I do a read, maybe I don't see. I do another read, maybe I don't see. Eventually, I will see it, and then I will always see it. That's much nicer than eventual, because in eventual consistency, you could see it and then not see it, and see it and not see it. You might say, oh, that's very extreme, but it can happen. in a distributed system because you have failures, because you have stragglers, because you have congestion. These are possible executions, okay? So eventual consistency is really a place where you can think about interaction points and make things go better, okay? Okay, so let me make some conclusions and then make a challenge for this community. So first of all, programming, of course, requires real-world interaction. Programming is like poker and not like chess, okay? Especially for distributed programming, it's really essential. It's the name of the game. Second point, functional programming is the best paradigm. It's clear. You can do, it has so many good properties, but it does not support real-world interaction. Imperative programming does, but it drops the advantages. So the solution is to do them both, but in the right way, and have a nice notation. So you use functional programming by default. You add the interaction points where you need them, where you want them. So basically, you live in the pleroma, functional programming, timeless, the ultimate unknowable God, so you're in the right place. But since we're actually in the observable universe, you can't avoid time, so you have to add interaction points. And the third part is that you need a notation to let you think clearly. So simple design language, like I just showed you, very simple, no baggage, just getting to the point. Okay? So this is all work in progress, huh? What I'm telling you now is like the current state of our thinking. We're still working on this. We're still trying to figure out how to formalize and then applying it to more and more distributed systems. So now I want to make a challenge for this community. That design language I just introduced to you here, you could take Erlang as the base, make some changes, and turn it into that language. But the basic problem in Erlang, okay, Erlang's not perfect. It's good, but not perfect. The problem right now is that each Erlang process is an interaction point because it can receive messages non-deterministically. So that's actually the wrong default from the viewpoint of the ultimate pleroma, etc. That's the wrong default. What you really want is that the processes should be deterministic, should know where the messages are coming from, except where you don't want to know that. But by default, it should be deterministic. And if you do that, then Erlang will become essentially the perfect language for building distributed systems. So you're very close to perfection, but still a small step to be taken. Okay, so that's all. Thank you. I hope this was intriguing for you. So if you have any questions, I'll try to answer them.
So, questions and answers. Who would like to start?
Ooh.
We have 2 mics,
Ooh.
but no questions.
In computer science, the Turing machine is the holy grail. Huh? Isn't it time it gets replaced by the interaction machine?
By the attraction machine?
Interaction machine.
Interaction machine.
Yeah.
Yeah, I mean, Alan Turing was a product of his time. Huh? So he invented the Turing machine because it was really, really simple. But around the same time, even before Turing, the Lambda calculus was also invented. Huh? It was like in the 30s or something. Mm-hmm. So the Lambda calculus has much more stood the test of time than the Turing machine. I think the Turing machine is just a proof of concept. It's the functionality. But I think in a sense you're right. I think Lambda calculus, which is programming without time, should be the basis. And then we should think about how you add time to this. So this is kind of the problem with the functional programming community. They have this, I don't know, I mean, maybe it's changed by now, this distinction between pure and impure, okay? Pure is good, impure is bad. So there's this value judgment. But impure is not bad, it's just the real world. Programming is not mathematics. So you have to do it in a nice way.
Your answer basically confirms my point in a way that Turing machine is a model for computation.
Yeah.
And if you put interaction points in there, you need more.
You need more. Yeah, exactly. This is true.
Actually,
Yes.
And actually, this is
Yes.
not a widespread
You
understanding.
need more because computation by itself is just pure mathematics.
Yeah.
But programming is not just pure mathematics. You need more. Exactly.
And this should become much more common knowledge, I think.
It should, yeah. Exactly. Yes. Absolutely.
More questions?
So is one way of making Erlang more ideal from the interaction point of view in that would it be that messages sent only from one-to-one mapping of
One-to-one would
one sender, one receiver?
be you can do one-to-one. I mean, the real point is that whenever you receive a message, you have to know where the next message is coming from. You should not have nondeterminism. Timing should not affect the result. So you can receive messages from multiple guys as long as you know which one is the next one. That's maybe they're alternating or simultaneous, two groups of two. That sort of answer? Yeah.
Yeah, thank you.
Yeah.
Got one over here.
Hiya. So the idea that failure is an interaction point,
Absolutely.
and Erlang programs are often designed with the idea that any process can fail.
Yeah.
So we will have to drop that as well.
No.
No?
I mean, of course, you have to. You can't avoid it. Like you can't avoid time. What you have to do is manage it well. Erlang does a pretty good job. You have to hide the failure, basically. You have to, if there's a point where there's really an interaction point that you can't avoid, the best is to somehow encapsulate it so it's hidden from the rest, so everything looks pure. So it's doing like things like supervisor is actually is giving you the basic elements for this kind of an approach, absolutely, for handling failure.
Yeah, I think we have time for one final question. So please.
You say the process should know who is sending the next message, right? Is it about knowing the order? Because in some business case, the server can change the reality. Say, this happened before this. And then you're consistent.
Yeah, you can change the order if it doesn't affect the final end. I mean, if the program knows, if the program is in control, you can't let the result depend on the scheduler, which is the real world, the timing. If the result is determined completely by the program itself, even by changing order, if it's the program that does it, it's okay. Then it's not time. Then it's not programming with time. It's coming from outside, then it's an interaction point.
All right, ladies and gentlemen, Peter van Rooij.
Okay. Okay.